Right. Okay. Can I put our video now? I think that it is streaming. So good morning, Brazil. I'm going to put it there. Welcome, everyone. Are you hearing? It's not.
It's not okay. Playing. This
I'm going to put now. I know what is it.
Que dividir sem raciocinar. Na vida é sempre bom multiplicar. E por A mais B eu quero demonstrar que gosto imensamente de você. Por uma fração infinitesimal, você criou um caso de cálculo integral. E para resolver este problema, eu tenho um teorema banal. Quando dois meios se encontram, desaparece a fração. E se achamos a unidade, está resolvida a questão. Para finalizar, vamos recordar que menos por menos dá mais amor. Se vão as paralelas ao infinito se encontrar, por que demoram tantos corações a se integrar? É que infinitamente, incomensuravelmente, eu estou perdidamente apaixonada por você. Pra que dividir?
Thank you, everybody, for coming. I would like to congratulate every mathematical woman for the International Day of Women in Mathematics. And to start our celebrating day, I'm going to pass the word to Jacqueline to introduce our host.
No, it's for Patricia.
No,
yes.
If you want to tell some words to us.
Okay. So, well, I think you said already. Good morning to everyone. Good afternoon for who is not in Brazil. And welcome back. Welcome everyone that is also on YouTube. And congratulations for us. It's a nice day. It's a day of being happy. It seems that we are not so filled. We've been showing this in this conference. We are a bit spread through the world, but And in our local place, seems that we are a bit lonely, but it's not that much. There are plenty of nice women doing very good math. And thank you everyone for being participating on the celebration. I pass for Patricia, who is going to introduce our speaker for today.
Thank you very much, Jacqueline. And it's a great pleasure to me and an honor to introduce Sophie Grivaux. And I'd like to acknowledge, to thank for her to accept to talk in this conference. It is an honor for us. Sophie Grivaux is a researcher at CNRS France. She is also a professor at the University of Lille. And we met first time, so we met in an online conference, so last year in linear dynamics. And I hope we can meet her in Brazil sometime in the next conference. So it's a great honor. And so she's going to talk us about some dynamical systems and related to functional analysis, which is her main topic of research. Thank you, Sophie.
Okay. Thank you very much, Patricia, for the nice introduction. And thank you to all of you for this kind invitation. As I was saying to Jacqueline, Patricia, and Luciana, when I first joined the session 15 minutes ago, I mean, it's very nice to be able to be with you, even if it is remote. So hopefully someday it will be a real live meeting. So as Patricia said, I'm going to talk to you about dynamical systems, but more specifically some dynamical systems which are most important in functional analysis, so which are the so-called linear dynamical systems. So my talk will be really basic, I would say, and I will begin by introduce some general features which are common to all people working in dynamical systems. So if you're already an expert in dynamical systems, you will probably be a bit bored, but I try to target a wide audience. So I will see how it goes, and then we'll move over more specifically to the linear setting and see, well, what we can say, which is interesting in the study of recurrence properties. Okay, can you see my screen well? Is it okay? Yes?
Yes.
Fine. Okay, and then also don't hesitate to interrupt me, okay? We're on Zoom, so perhaps it's not so easy to interrupt as it would be in a real life talk, but please do it. It's nice for the speaker to have a feedback. So I'll be very happy if you interrupt. Okay, so now I should present this a bit better. Yes. Okay, so recurrence properties in linear dynamics. So as I told you, we will begin from the start, actually. So what is a dynamical systems? So I guess you heard it a lot on the topical session on Tuesday. So a dynamical system is a pair consisting of a space X and a map from X into itself. And the general aim, if you look at dynamical systems in general, so it's a very wide area, but in general, one can say that the general aim is to study the long-term behavior of the iterates Tn of T. That is, you take T, then T times T composed with T, that's T2, T composed with T, that's T3, etc. And then you try to see, well, when N, which is the time, grows to infinity, what's happening and how does the system behave in the long time. So, okay, if you want to be able to say something well, you have to have some additional structure, right? It's difficult to say something with very, very general hypothesis. So there are roughly two kind of assumptions which you can put on your space and your map. The one being topological, I'll talk about that first, and the second concerning measure theory. So that will be the second thing. So the topological point of view, it's the following. Well, you suppose X is a topological space, and in my talk, even if I don't say it every time, it will always mean that X is a complete separable metric space, right? So that's more or less the general setting of Polish spaces. So I won't suppose that the space is compact, which is sometimes a rather standard assumption when you're doing topological dynamics, but rather that it is complete separable metric. And then the natural assumption is that T, which is a self-map from X, is a continuous map. And then, well, you have the very well-known notion of the orbit of a point X sitting in your space, which is, well, you consider the action of all the iterates of T on this particular point X. And that's a subset of your capital X, which you call the orbit of X under the action of T, right? And, when you have that, then the general goal when you study dynamical systems from the topological point of view is to look at some natural properties of orbits. So natural can mean quite a variety of things, right? Depending on what are your interests, what you're working on, etc. So here I recalled some rather basic points of interest when you're looking at orbits. So a first very natural thing is, well, looking at periodic orbits. So I rewrote the definition here, but it's very natural and well known. A point is periodic if when you iterate it under the action of T, then it comes back to itself after a finite number of times, right? So you get a periodic point this way. Then, well, it's also very natural. So these are rather small orbits, right? The orbit is finite, so it's a small set in your space. And then from the opposite point of view, you can ask, well, are there orbits which are large, in a sense? Of course, in general, unless you're in the particular context of a countable space and so on, your orbit cannot be equal to the whole space, but it can be dense. In many situations, it can be dense in the space. So having a dense orbit means that you have an X such that whenever you take an open set which is non-empty, then after some time, which may be very long, but sometime you come back to U, right? So that's a dense orbit. And then, well, since we're working in a complete separable metric space, the Baire category theorem is at our disposal. And this implies that the existence of a vector with dense orbit is equivalent to a global property of the dynamical system, which is called topological transitivity. So topological transitivity, I wrote the definition here. So it says that whenever you take two non-empty open sets, then you can travel from one set to the other in a finite number of steps. Of course, so Tn of u is not equal to V, but it intersects V for some n. So this is a characterization which may be very useful because, well, if you want to show that some orbit is dense, then you have to be able to pick the orbit. Right. And in many cases, well, it's not so easy to write down a vector and say this particular vector is going to have dense orbit. Of course, when you're doing symbolic dynamics, then it's rather transparent. But in many other contexts, it's not so easy to pick a vector or a function with dense orbit. But when you have this characterization in terms of topological transitivity, you're working on sets. And when you have this property on open sets, then it tells you that, well, I have vectors which have a dense orbit and even a dense G delta set of vectors with dense orbit. So in case you're not familiar with the definition, let me say that what I call a G delta set is a countable intersection of open sets, right? And the Baire category theorem tells you that in a complete separable metric space, or it could be more general, but in this context at least, then the intersection of a countable collection of dense open sets is dense. That's the Baire category theorem. And then, well, I just wrote that for culture. Somehow I won't use it in my talk. But when you have topological transitivity and a dense set of periodic points, you have a system which is called chaotic in the sense of de Vennet. So if you go back to, if you know the classical definition of de Vennet counts, you also have the property which is called sensitivity to initial conditions, which says that, well, if you start from 2 points which are very close to each other, then you may end up the trajectories may be widely different, right? But then it's a theorem due to Banks and co-authors that actually, as soon as you have topological transitivity and a dense set of periodic points, then you have this de Vennet chaos, right? So something which it's a bit funny because the feature of the de Vennet chaos, which is most easily remembered, that is this sensitivity to initial condition, is actually a consequence of these two other properties. Okay. Sorry. And then, well, so some other natural property of orbits, and which is the one which will interest me most in the talk, is that of recurrence. So recurrence is very easily defined. You say that a point is recurrent if there exists a strictly increasing sequence nk of integers such that tnk of x goes to x as k goes to infinity. Right. So the word recurrence is very appropriate. It means that, well, I have my point x. If I take a very small neighborhood of it, I will get back to it with the orbit and as close as I want, actually. So here it's written in terms of sequences. That's exactly this definition. And I will denote by rec or REC of T, the set of recurrent points of T, and it's always a G delta set, that is a countable intersection of open sets. And well, I wrote it so that if you have never seen this, you may not be lost, but it's really straightforward. Saying that a point is recurrent is saying that for any epsilon and any n, you can find a time, small n, greater than your capital N, such that Tn of x is epsilon close to x in terms of the distance, right? So this d is the distance. If you remember, I'm working on a complete separable metric space, so d is the metric actually on the space. So it quantifies how close Tnx is to x, right? Okay, and then there is a definition. So this definition is important for the rest of the talk because perhaps it is not so natural, or perhaps other people use the word recurrent in a different sense. But for me, in this talk, saying that T is recurrent means that the set of recurrent points is dense in X, right? It's not saying that there exists a recurrent point. Right? It means that the set of recurrent points is dense, right? So perhaps it is not the best term. I mean, that can be discussed, but that's what I will use in the talk. So I'll try to recall it as we go on. But for some theorems, if you think of recurrent as just existence of recurrent point, you will be lost, right? So there is density in the picture. Okay, and then, well, here is an example with which you're certainly familiar if you're working in dynamical systems, that if I have a continuous transformation of a metric space, then it always admits a recurrent points. The recurrent points may not be dense, but there exists a recurrent points. And this follows from the existence of a so-called minimal subsystem that is a minimal closed set for the system. Okay. Okay, so that's so you see, it's very basic. That's what I wanted to introduce on the topological point of view. And now, if we want to talk a bit about the measurable point of view, then here we shift a bit the setting and we assume that X is a probability space. So there is X, there is a sigma field B, and there is the Borel measure B. And I will always assume that it is a probability measure, right? There is plenty of work done in linear dynamics with measures which are not probability measure, right? So but here in my talk, whenever I say measure, I mean probability measure, right? There won't be anything else. And then my transformation T, then, well, it's quite natural to assume that it is measurable, right, with respect to the sigma field. And we also assume that it preserves the measure in the sense that whenever I take an element A in my sigma algebra B, then the measure of T minus 1 of A is the measure of A, right? So that's the very classical definition. And then, of course, in this setting, well, when we're in the topological setting, well, it made sense to look at the behavior of one particular orbit. Here we are in a measure space, so it doesn't make sense that much, but it quite makes sense to wonder about the long-term behavior of mu almost every orbit of T. Right, so that's the points of the classical theorems in ergodic theory. And well, I'm recalling here the definition of an ergodic transformation. So as you know, an ergodic transformation is a transformation which is indecomposable. Right, you cannot break your system into two pieces on which your transformation T would act independently. So if I want to formalize this definition, it runs as follows. Whenever I take an A in B, then if T minus 1 of A is equal to A up to a set of measure 0 for the measure mu, then it means that either A is the whole space in terms of measure, that is the measure of A is 1, or it is essentially empty, the measure of A is 0, right? So that's exactly this indecomposability property that ergodicity means. Okay, and then I wanted to present, to quote these two important theorems in measurable dynamics. So the first one is the Poincaré recurrence theorem, which tells you that in this context, if you take a set of measure 0, then this set goes back to itself on a part of positive measure. So formally, it means that for some integer k, T minus k of A intersects A on a set of positive measure. And it's a rather standard argument to say that, well, when you have that, then mu almost every point in your A is recurrent with respect to T in the sense that it goes back to A in finite time. Okay, so, you know, the word recurrent is, well, I don't know the English word for it, but it comes back very often in mathematics and especially in dynamical systems. So actually here it's not exactly the same as what I said in the topological context, but I think you understand the meaning. So we'll see in the next slide the links between topological recurrence and measurable recurrence. But here that's the natural notion of recurrence. And then I recall the Birkhoff pointwise ergodic theorem, which tells you that when you have an ergodic transformation for mu almost every x, the time means converge to the space means. That's how you could say it in a condensed form. So concretely, it means that if you take an integrable function on your space x, then you apply your function f to all the elements of the orbits of x. And then when you take the Cesaro means, then this converge to the mean of f with respect to the measure mu. So particularly it converges to something constant, right? So that's this averaging theorem, the so-called ergodic theorem. So, well, I think, well, if you're working in dynamical systems, everything of this is really very well known. But if you're not working in dynamics, well, it's a very, very quick overview of the main ideas actually in the theorem. Okay, so now we have these two contexts, and of course, what's interesting is to put the two together, right, and see what happens, and well, what measure has to say about topological properties and so on and so on. So, well, if we want to put the two together, then first we have to put together the two assumptions, right? So we have to assume both that X is a complete separable metric space, that's for the topological point of view, and then we consider only the sigma algebra of Borel subsets of X and mu Borel probability measure on X, which is T invariant. Right. So that's the proper context where you have both topological properties and then a measure defined on the Borel set. So it's kind of compatible with the topology. And so you can look at your dynamical systems from the 2 points of view. And then it's not so difficult to prove that in this case, the measure of the recurrent points for T is equal to 1. Right. So it's a mix of the Poincaré theorem and using open sets and so on. So this is very well known and done, for instance, in Furstenberg's book on recurrence. But if you look at this statement, then it's in a simple context, of course, but it's exactly the kind of statement we want, because we are in a topological setting, let's say, and using an hypothesis we have on a measure, we can deduce, for instance, that my transformation T has plenty of recurrent points. Right. So we start from a topological assumption, we have a measure, and then going through, we get a conclusion on a topological property. Right. So if your measure has full support, which means that for any non-empty open set, the measure puts some mass on this open set, the measure of U is positive, then your operator is your transformation. For the moment, it's not an operator. Your transformation is recurrent, which means it has a dense set of recurrent points. Right. So that's a first kind of baby example where, measure theoretic dynamics have something important to say about topological dynamics. And then here is another example. If you have a transformation which is ergodic with respect to mu, then let's see what happens when we apply the Birkhoff ergodic theorem to the indicator function of a non-empty open set in the space X. So what does it say? It says that if I take the Cesaro means of the indicator function of U applied to T and X, it goes to the integral of the space of the indicator function of mu against the measure mu, and that's the measure of U, right? So I'm not happy about this last sentence because the definition is on the next slide. So this is a bad point for me, sorry. But what this is saying is that, okay, if now I fix a capital N and I look at the set of integers sitting in this interval 1 to n, which are going to U, T and X is going to U, then if I look at the set of such integers, then it has positive density in the sense that the Cesaro means go to something which is positive as soon as the measure puts some mass on U, right? So even if you're not familiar with the definition of positive density, and this will be hopefully on the next slide, then the intuition you can get from that is, okay, this set is very large, right? And it tells you that under this assumption, so something ergodic with respect to mu and U which has positive measure with respect to mu, then the set of integers n such that T and X is going to U, is sitting in U, right, is large, right? So that's something which will be important to us. Right. Okay, so my definition is not on the next slide, but I promise you that it will be somewhere on some slide afterwards. Okay, so that was the general introduction, so no assumption essentially on the dynamical systems. So now some of the dynamical systems which interest me very much are the so-called linear dynamical systems. So what is it? This corresponds to the case where your space X is a Banach space, or it may be as well what is called a Fréchet space. So well, if you don't really know what is a Fréchet space, I mean, we'll just stay in the Banach space setting. We'll see some examples afterwards. And UT, then, it has some compatibility with the linear structure of X, of course. And so we assume that it is continuous, or we often say bounded, linear operator on X. Right. So this is why we call this linear dynamical systems. And well, that's a dynamical systems. And as I've been talking about, then we can study it from the topological point of view or the measurable point of view. So the topological point of view, that's exactly what I said previously. You take a vector X, very concrete, you take the orbit, and you're looking at properties of the orbit. And then the measurable point of view, theoretically at least, it's also simple. You're saying, well, I have my bounded operator on X. Can I find a t-invariant measure? So it has to be interesting, right? Because if I take the Dirac mass at 0, since t of 0 is equal to 0, I always have a very nice invariant measure, but it won't ever tell me anything interesting about my system, right? So when I talk about interesting invariant measure, it has to have some substance somehow and not to be the Dirac mass at 0. And then if by chance I manage to find such a measure, then we can look whether the transformation is ergodic with respect to it, or even if you know the terms weakly mixing, strongly mixing, what's happening, etc. Right. Okay, so that's sorry, that's the general setting, and of course it's good to wonder if it's likely to have some interest, right? So. When you look at it for the first time, you're tempted to say no, because if you think at a finite dimensional case, right, UT is a matrix on, let's say, Rn or Cn. And, so, of course, you can ask yourself the question, well, what about the iterates of the transformation, so the powers of the matrix, how are they acting on the vectors? So, actually, in the finite dimensional setting, you can know everything about the behavior of the orbits. For instance, if you're in the complex case and you're given a matrix, then you can put it in Jordan form, right? So you have to care only about the Jordan blocks. And then you can compute the iterates of a Jordan block. And if you're given a vector, you're able to decide whether the orbit will go to 0. That's what's happened when the associated eigenvalue has modulus smaller than 1, or if the orbit goes to infinity, or there may be a rotation. So you have to be careful. It's studying the different cases and also do the real case, but you can say everything, basically. So it's not so interesting once you have done this study. Well, it's done, and then there's nothing more to do. But if your space is infinite dimensional, and we'll assume that it is separable, then it becomes much more interesting because, there are plenty of things which you don't know and which your transformation may behave very, very differently from just matrix. Right. Okay, so let us have a look at some basic examples. So my first example of a space is the space of holomorphic functions on the complex plane. And it's endowed with the topology of uniform convergence on compact sets. So this is not a Banach space, right? This is typically a Fréchet space. So you have a vector space, which is locally convex, and it is endowed with a distance, which is a translation invariant. And with respect to this distance, it is complete. But on such a space, right, you can define what are continuous linear operators. So there are two kind of standard and very natural examples. The first one is the derivation operator, and the second ones are the translation operators by a vector which is non-zero, of course, else you get the identity operator. And it's known since the last century that these two operators are hypercyclic. This is due to MacLane for the derivation operator and to Birkhoff for the translation operator. And saying they're hypercyclic, that's an important definition, I should have put it in red, means that they admit a dense G delta set of vectors which have a dense orbit. So being hypercyclic, it's actually the terminology in linear dynamic for having a dense orbit. And if you recall the criterion for topological transitivity, as soon as you have one dense orbit, then you have plenty of them, and you have a dense G delta set of vectors with dense orbit. Right, so this is the first example, and it was initially proved using methods from complex analysis and the Runge theorem and so on. Nowadays, we we prove it in a kind of more algebraic way, but that's using the Birkhoff transitivity criterion. But still, there remain important examples in linear dynamics. Then, my second example is in the Banach space framework. So it's the simplest of Banach space, the Hilbert space, L2 of n. So just in case I recall the definition, so it's the set of sequences of complex numbers which are summable with respect to the norm which I wrote here. So the sum of the squares of the modulus of xn, and then I put a square root over the whole. So that's the canonical norm on L2 of n, which turns it into a Hilbert space. And this space is endowed with the canonical basis En, and En is the sequence with zeros everywhere except 1 in the nth place. So it's a Schauder basis actually of the space, but it's in the Hilbertian case, it's a Hilbertian basis as you're used to. Okay, and then on this space, I define an operator B. It's B because of backward. It's called the backward shift. So it shifts a sequence one step to the left. So if I define it on the basis vector En, it maps E0 to 0 and En to En minus 1 when n is greater than 1. Right. So it would be good to have a blackboard here, but if you have a piece of paper in front of you, if you've never seen this operator, just write it down in matrix form with an infinite matrix and you'll see very well what happens. So then, of course, this operator B has no chance to be hypercyclic, to have a dense orbit, because the unit ball is invariant by this operator. If I have a vector of norm 1, then B of this vector is of norm less than 1 as well. So then it has no chance of having a dense orbit because all orbits remain bounded, actually. But if I multiply the operator by a number of modulus greater than 1, then it becomes hypercyclic. So it has vectors with dense orbit. It has plenty of periodic points, which are actually eigenvectors associated to eigenvalues, which are roots of unity. So they're even chaotic in the sense of Devanny. And moreover, they admit invariant probability measures with full support, with respect to which they are ergodic, even strongly mixing whatever you want, actually. So if you, I put this example here because when you're looking at when you want an operator which has very nice properties and is doing everything you want in linear dynamics, then the first example is this one, right? And you can really work on this operator and understand what's happening. And unfortunately, time is a bit short for proof, so that's a bit frustrating. But one of the ways you can understand why this operator has such a nice property is that it has plenty of eigenvectors. So it has plenty of eigenvectors of modulus smaller than 1, some are of modulus greater than 1, and also some are of modulus equal to 1. And actually, these eigenvectors are enough to have some very nice topological properties like hypercyclicity, chaos sometimes if your eigenvalues have roots of unity, and also having invariant probability measures with full support is something which is, at least in the Hilbertian setting, very much connected to the existence of plenty of unimodular eigenvectors. So of course that's a clumsy attempt to summarize a lot of theory in 5 minutes. But if you should recall just one thing from this talk, is that when you're doing ergodic theory for linear dynamical systems, you have to care about unimodular eigenvectors. Right. There are other ways, but that's a very efficient way to do it. And this idea of exploiting eigenvectors for operators was first introduced by Godefroy and Shapiro in the topological setting, so for hypercyclicity and chaos. In the measure theoretic setting, it's due to Fritzianis. And then I developed it further in collaboration with Frédéric Bayard, and we could obtain some characterizations and so on, but that would be a bit long to explain. Okay, so Now let me get to the main topic of my talk, which is what about recurrence properties for linear dynamical systems? So here the context will be that of Banach spaces, infinite dimensional, separable, and I will ask for X to be complex, right? Some of the results would remain true in the real setting, but for the purposes of this talk, it will be complex. So I have on this space a bounded operator T. I have vectors, small x in capital X. And if I am given such a vector, I will denote by this curly n of X the set of open neighborhoods of X. So since we're caring about recurrence, right, it's quite obvious that neighborhoods of X. So I'm sorry, there is a typo. It should be neighborhoods of small x, not of capital X, right? So sorry for the typo. Well, I think it's a rather clear one what should put here, but sorry. And then I will denote by nt of xu, so that's a notation I used previously already, the set of return times of my vector x to u, right? So it's a subset of the integers, and it tells you when my orbit is getting back to you. And then, well, here is the I define again in the linear setting the notion of recurrence, but of course it's exactly the same as what I said in the general context. So my point x is recurrent if for any neighborhood u of x, then this set is infinite. So we could say it's non-empty, but actually since we can decrease the neighborhood as much as you want, it's exactly the same as saying it's infinite. And this definition and the subsequent study of recurrence properties in linear dynamics was first made by Kostakis, also Manoussos Parissis, in two important papers on recurrence, so where they started a systematic study of recurrence in the linear setting. So we will say a few words more about just simple recurrence afterwards. But my interest in this talk will be to somehow strengthen these notions of recurrence by requiring that the set of return time is not only infinite, but it's large. So, for instance, here's my first definition, that the vector x is upper frequently recurrent if for any neighborhood of x open, then not only does x return to you infinitely often, but it returns to you on a set of positive upper density, so a large set. And what is positive upper density? If you have a subset A of n, the positive upper density of A is the lim sup of 1 over n times the cardinal of A intersected with the segment 1n. So you take capital N, you intersect A with this interval, you look at how many points you have in it, you divide by n, and you take the lim sup as n goes to infinity. So it tells you that at some times arbitrarily large, when you look at the times where Tn of x is going to be in U, then it will be a positive proportion of your interval. Not for all intervals, but for some intervals arbitrarily long. That's what it tells you. And then you also have the notion of frequent recurrence. So it's exactly the same definition, but here you required that the lower density of ntxu is positive. So lower density, instead of taking a lim sup, you take a lim half. So it's something stronger because you require that on every interval sufficiently large, then you have, let's say, 1/4 of the time where you land in your open set U. So when you take upper density, you may have plenty of times where you're in U, then a very, very long gap, and then again plenty of times, and so when you take the whole interval, it's still large, and so on. When you take the lower density, then for n sufficiently large, it's in all intervals 1n, then you have some proportion of the orbit which are sitting in U. And then even stronger, you have the notion of uniform recurrence, where you ask that the set of return times of x to u be synthetic, that is, has bounded gaps, right? So for instance, if you take an interval of length 100, any interval in the set of positive integer, even if it is very much shifted to the right, then at some point in this interval, your orbit will return to you, right? So these definitions were introduced and studied in detail in a work by Antonio Bonilla, Carl Grosse-Ernmann, and Antonio Lopez Martinez and Alfredo Perez. So Antonio Lopez Martinez is my co-author in the work I'm presenting. I wrote it on my introduction slide, but I forgot to mention it explicitly. So that's the time for doing it, that it is joint work with Antonio Lopez Martinez. So they introduced this notion of upper frequent recurrence, and uniform recurrence. And then there is the formal definition. Then an operator is called, let's say, frequently recurrent if it has a dense set of frequently recurrent vectors. So there is still this density assumption, right? And then you can make up the definition for any strong notion of recurrence. So that's what I mean by the operator T is called something recurrent if it has a dense set of something recurrent vectors. And of course, uniform recurrence implies frequent recurrence, implies U frequent recurrence. So that's upper frequent recurrence. The U is sitting for upper, and it implies the standard recurrence. And now I can get to the questions we asked ourselves with Anthony. I mean, so it stems from this paper with 4 authors, which I quoted on the last slide. So the questions are, in a sense, very basic. When we have a certain recurrence property for linear dynamical systems, can we say that, in fact, we have a stronger recurrence property? Right. So, if, for instance, I mean, could it be true for some reason that when you have an upper frequently recurrent operator, you have a frequently recurrent operator, whatever, or even more? I don't know. So, this kind of question. So here, so what I'm going to say is only partly true, as you will say afterwards. But the idea would be that. Sometimes, when you're working in linear dynamics, the fact that you have a linear operator on a Banach space, it's something very strong in the way of structure. And it may help you to get results of this kind, which would not be true in the nonlinear setting, right? Where you could construct all kind of weird examples where you have continuous maps which twist the thing in a way which tell you, okay, it's hopeless and it won't work, right? So that's the idea. And one of the things also which are very nice when you have linear operators is that you may have eigenvectors, unimodular eigenvectors. And then where you're thinking, okay, I have a vector such that Tx is equal to lambda x for some lambda of modulus 1, then you have this observation, which is very, very well known, that if you take some points in lambda 1, lambda k in T, which is the unit circle, so there are complex numbers of modulus 1 and a certain epsilon positive. Then if I look at the set of integers, so I'm very sorry, there is a typo again here. So it's a set of integers n such that the supremum for j between 1 and k of lambda g to the n, sorry, it's to the n and not to the k, is epsilon close to 1. So it's the set where if you consider all rotations by lambda g on the unit circle, then all orbits are epsilon of 1, are epsilon close to 1, so of return times to 1. Then this is a synthetic set. It has bounded gaps, right? So this is a very large set. That's what you should recall. And so actually, so here is a short proposition that if you have an operator such that its unimodular eigenvectors span a dense subspace of X, then it is obviously recurrent. It is uniformly recurrent, right? And well, I wrote down the short proof just well, so that you may get a feeling of the thing. It's not difficult at all, really. How does it go? So you have your unimodular eigenvectors xj with eigenvalue lambda j. So T of xj is lambda j xj. And in any non-empty open set, you can put a vector which is a finite sum of the form sum of AG xg, right? For some AG, for some xg. And then if you look at Tnx minus x, then you have linearity, eigenvectors, etc. You can compute exactly the sum and then bound the norm of Tnx minus x thanks to the triangular inequality, right? And you get that it's less than the sum of modulus of Ag times the norm of xg. And then, well, what remains is what you expect, the supremum of lambda j to the n minus 1, where j runs over 1, 2, 3, etc. to k. And then this is what I wrote in the previous slide. The set of n's such that the supremum is smaller than epsilon is synthetic. So it yields that the set of integers n such that Tn of x is epsilon close to x is synthetic as well. And that's exactly the definition of uniform recurrence. So you have a dense set of uniformly recurrent points and you're done. Right. So it's a very straightforward argument, but it's something which is specifically linear. Right, so this is one of the reasons why I wrote it down. Okay, so what did we prove with Antonio? Here is our first result. So if we have a reflexive Banach space and a bounded linear operator on X, then actually we can improve on recurrence. Saying that T is upper frequently recurrent is the same as saying that T is frequently recurrent, and it's also the same as saying that T has an invariant measure with full support. So let me comment a bit on the assumptions of this theorem. So if you don't know what is a reflexive Banach space, you just imagine it's a Hilbert space, right? The point of the space being reflexive, we'll see it in the proof, is that, for instance, if you take the closed unit ball, it will be compact with respect to a certain topology, which is called a weak topology, which is weaker than the non-topology on X. So that's why the assumption is here. Right, and so you see this theorem, as I promised you, it's an improvement, right? If you start from an operator which is upper frequently recurrent, you don't see from scratch any reason why from your orbits returning to U with a set of positive upper density, you could somehow get something with positive lower density, which is much stronger, right? And the idea is actually what I tried to advertise in the first half of my talk, that in order to prove a statement like this, so suppose you want to prove the equivalence between 1 and 2, if you try to do it in a purely topological way, then I don't know how to do it. But if you go through measure theory, and that's why you have the 3 here to help you with it, then it becomes much more transparent. So you have to go through measure to get something topological. Okay, so how do you prove something like that? So, okay, I think you agree with me that if you have frequent recurrence, you have upper frequent recurrence, right? So that's just definition. Then going from 3 to 2 is somehow rather standard also. So you have to use some machinery from ergodic theory. So if you have an invariant measure with full support, you apply the ergodic decomposition theorem. So it's a theorem which tells you that, well, it's written in its name, but that when you have a T invariant measure, you can write it as a kind of integral of ergodic measures with respect to your transformations. And it tells you in particular that if you have a non-empty open set, you can find an ergodic T invariant measure which also puts some positive mass on you. This is all what we will use, but it tells you that. And then you do some kind of cooking with the Birkhoff pointwise ergodic theorem. You obtain that the set of frequently recurrent points for T has measure 1, right, with respect to your measure. And so it tells you at least that T has a frequently recurrent point sitting in U. And since you can do that for any non-empty open set, then you get that your operator is frequently recurrent, right? So that's how you do it. And so now what remains to be done is to prove, so what do I have to prove is that 1 implies 3. So if I have something which is U frequently recurrent, then I have an invariant measure with full support. And okay, so this is a statement which is valid outside the linear context, right? On a rather wide class of Polish dynamical systems. But here I'm presenting it only in the linear setting. And well, that's how the proof goes. You start from, so it should be a U frequently recurrent vector, sorry, but it doesn't change anything to the proof, basically. You take a ball around x0, and then you know that since your set NT x0U has positive upper density, then you can find a sequence nk of integers strictly increasing such that the means which I wrote on the slide are converging to some alpha which is positive, right? So it visits the orbit of x0 visits U on a set of positive upper density. That's rewriting the definition. And then, okay, you can consider a natural collection of measures, which are the sum, the means of the sum of the Dirac masses at the point of the orbits, right? And then what would you like to do? If you're trained in compact dynamics, you're saying, okay, I have a sequence of probability measures on a compact space, then I can extract a subsequence which will converge to some measure, and then I will get a measure which will be T invariant and things which work nicely and so on. So here, unfortunately, I mean, I'm in an infinite dimensional Banach spaces, so, you know, bounded closed sets are not compact. So there is no way you can go this way. But since my space is reflexive, if I take a weaker topology, so a topology which has less open sets, which is called a weak topology, then it so happens that, well, sorry, all bounded closed convex sets in X are compact. So I'm sorry, there were a few typos, but this one is bad because it's mathematically bad. So it should be all bounded closed convex sets in X are compact for this topology. So in particular, closed balls are compact. So I wrote down the definition of the weak topology in case you've never seen it. If I have a sequence of vectors xn, it converges weakly to X if for any continuous functional x star of xn goes to x star of x. And then, so there is work to be done. But once you have compactness for this weak topology, you can more or less mimic the argument in the compact setting, say that you have limit points for this collection of measures, and it yields a T-invariant probability measure, which puts some mass on you. And then, well, you take a mean of the measure and so on. And then it's plain sailing, right? So that's what we proved in this setting, that we can indeed improve on recurrence by connecting it with meshes. Okay, and here is my last slide. I will be quick because I'm late. I'm sorry. So it's a second result we proved with Anthony. And the second one is really specifically linear. So now it's in the Hilbertian setting, and we don't know if it's true outside of the Hilbertian setting. So we have a complex separable infinite dimensional Hilbert space, a bounded operator on H. And this is a characterization of uniform recurrence. And it tells you that an operator is uniformly recurrent, so it has a dense set of uniformly recurrent points, if and only if the span of the unimodular eigenvectors of T is dense in H. Right, so that's a very concrete characterization, right, in this linear setting. So, of course, 2 implies 1 is straightforward. That the proposition I showed you on one of the previous slides, that if you had a finite linear combination of unimodular eigenvectors, you got a uniformly recurrent point. And then in the reverse direction, that's where the work is. If you have something, an operator which has a uniformly recurrent vector, you can build a measure from it, thanks to this theorem. Because for a point being uniformly recurrent is much stronger than being frequently recurrent. So you indeed have an invariant measure. But moreover, you can construct an invariant measure with full support, which has a so-called second order mean. So it may look like, well, it's not so much to add, that it's something important, because when you have that, you can conclude, but by a rather standard machinery, that it admits an invariant Gaussian measure with full support. So I have no time to give you a definition of a Gaussian measure, but you certainly know the definition of a Gaussian measure on the real line, or on the complex plane, or on Rn or something. And that's a generalization to the Hilbert space, but these measures are extremely concrete. You can get your hands on it and work. And so it happens then whenever T admits an invariant Gaussian measure with full support, then the span of its unimodular eigenvectors is dense in H. So this was first suggested by Fritianis, and we proved it in detail with extensions by with Frédéric some long time ago. And so using here the Hilbertian structure and uniform recurrence gives you rather neat characterization of uniform recurrence. So we could do some further things along these lines, but I think these are the main ideas that, well, when you want to improve on recurrence properties connected to eigenvectors and so on, measure theory and ergodic theory proves to be a very useful tool. Okay, so I think I'll stop here. Thank you very much for your patience, because I'm a bit late, and well, I think I'm finished. Thanks.
Thank you, Sophie. And let's thank the speaker. And you are not late. We started late, so it's really fine.
Yes, I couldn't
Thank you very much. Yeah, to celebrate. Yeah, it's fine. Yeah, thank you very much. And are there any questions for Sophie? There is someone on YouTube that is taking notes of the questions. I think some of the students.
Yes, but I think so far there are no questions on.
There are no questions.
I'm also checking.
I do have a question.
So
Yes.
please.
So you mentioned that the measures with full support are usually the interesting ones to study in the linear setting, the infinite dimensional setting. But I don't know, I've seen this in some places, and I always thought that these kind of measures were like too general, because the condition seems, I don't know, a bit too general, right? The condition. So I was wondering if besides the maybe the Gaussian measures, is there another class of interesting measures one can define or choose to work with when studying these properties in the infinite dimensional setting?
Yes, okay, so it's a very good question, actually. And you're quite right in your feeling. So actually, you know, Gaussian measures were the measures which were first studied in linear dynamics, because they're very concrete. You can get your hands on it, especially in the Hilbertian setting, and you can get characterizations in terms of if and only if. You know, I can tell you an operator admits an ergodic measure, let's say, with a Gaussian ergodic measure with full support, if and only if some properties on the eigenvectors. So that's very nice. But well, if you come to look at it, for instance, if you have, let's say, a fixed point or an eigenvector or whatever, you can build from it measures with compact support, which are very far from being Gaussians. And these measures and measures constructed from it and so on can prove to be extremely useful. So actually, I would say there is a life after Gaussian measure. And there has been a lot of work done with measures which were non-Gaussian. So for instance, if I want to give you a striking example, it's a result of Glasner and Weiss, which I could generalize afterwards. But the result I'm going to quote is due to really Glasner and Benji Weiss, that if you take, you know, these multiples of the backward shift, let's say 2b on the Hilbert space, then whenever you take any ergodic dynamical system, nonlinear, whatever, on symbolic dynamics, whatever, anything you like, then you can find a measure on the Hilbert space such that your initial dynamical system is isomorphic as a dynamical system to your 2b with your measure, right? And this measure, of course, is not Gaussian. It's much more complicated. right? So you're quite right in your feeling that Gaussian measures are not everything. I mean, there are a lot of works done with measures which are not Gaussians, of course.
Thank you.
I hope it answers the question.
Thank you very much. So, thank you very much, Philippe, for the question. Are there any other questions? No. But still on these questions, on this last question, is that easy to see cases where you have, what does it make sense to have Lebesgue measure?
Lebesgue measure, well, on a Hilbert space, you have nothing really similar to Lebesgue measure, because one of the important features of Lebesgue measure is that it is translation invariant. And as soon as you leave finite dimension, you cannot do something like that. So I don't know. I would say that, well, the simplest somehow, the closest you can get from this point of view would be the Gaussian measures.
Would be the Gaussian. So yeah.
That's what I would say. And already you can do a lot of things with that, but no, there is nothing really similar to Lebesgue measure, I would say, directly at least.
So thank you.
You're welcome.
Any other question? So if not, let's thank the speaker again.
Thank you very much.
Thank you very much for this nice talk.
Wow. Thank you, Patricia.
It was indeed a very nice talk. Thank you. And a very nice subject, actually. I appreciate it a lot. And we have some students here. I spot some students from the Federal University of Rio that they are interested in this subject. So thank you for the talk. I hope they enjoyed too.
Well,
it's a shame questions, but I hope they enjoyed. You did a job to talk also for students.
Okay,
yeah,
I hope
it's
understandable, and that's was the idea.
Yeah, so thank you. We have now, well, today is the International Day of Women in Mathematics. So we are quite happy and to celebrate. So we have a big day today in our conference. We have, for whom is registered, already received by email, a link for a movie. I think you have 72 hours to watch the movie, so you can watch when it's best time for you. Is the Revolution Generation. I didn't watch yet, I admit, but seems to be a quite nice movie. And we will have in the afternoon the continuation of the workshop, music and math. And after it, we will have a round table. So everyone is welcome. The round table will be in Portuguese. But before we finish the session, we have our tradition of drawing some gifts. And special today, we need gifts to celebrate our day. So I think Andressa have already, before she shared her screen, let me share what we are going to draw. First, we'll draw this book. So the first will be this book, An Introduction to the Kolmogorov-Bernoulli Equivalence, from two mathematicians, Brazilians, Gabriel Ponce and Regis Varão. It's an offer from SBMAC. And the second will be our well-known kit offered by FAPERJ. It's an eco bag and a notebook with our symbol, our logo. So Andressa, if you can help me doing everyone that is in the room, it's in the list of the drawings. So Andressa made the list. Everyone has a number, and now she's gonna. Whoa. 3, 2, 1. And the number is 8.
Lisandra.
Lisandra. Hi, Lisandra. You won You got the book. Great. I will write our email in the chat. So please write to us with all your information, including the zip code. And the next is going to be the kit. The number is 3, 2. Have some emotion. So
Nossa,
it didn't work.
eita, deu ruim.
Let's just have a bit of patience. Don't worry.
Sorry.
No problem.
Seven.
7. At least was a good number.
Juan
Juan Carlos. I think it's Juan Carlos Salcedo. It's our student.
Yeah,
So congratulations. Yes. So
thank you.
you're welcome. So for you, it's going to be easy. Just stop by our office. Either me or Luciana will be there.
Okay, thank you, Jacqueline.
Okay.
Mhm.
So thank you very much especially for Sophie, for very nice talk. It was a pleasure to meet you. As Pat said, we are hoping that we can see you maybe in the future. You have never come to Brazil, no?
No,
I'm hoping.
no.
But, yes, so it's a good place, I would say. Well, I shouldn't say.
I do agree. Yeah. We should invite her the next time in person.
Yes. We hope to have the opportunity to invite you in a near future. So thank you for accepting this invitation. And
Well, you're welcome. It was a pleasure for me to give this talk. So thank you to all of you.
Thank you. So good afternoon for you, Sophie. Good afternoon for who is in the North Hemisphere. Good morning, and see you soon.
Yes,
in another time. So bye everyone. Thanks,
Bye.
Patricia.
Bye bye. So thank you for inviting us.
Thank you.